Welcome to the Problemas channel Season 1, Episode 4, the episode in which we will dissect a solution of the problem S1M2. Before we do that, however, I would like to apologize to my viewers for a small mistake that I made in the previous episode, where in the solution of the second part of the problem S1M1, I made a small mistake by not counting the very first circle that was part of the solution of that problem, and I mistakenly claimed that the overall cost of the corresponding mathematical algorithm was 24. But because of this particular circle that was called CT, the overall cost of that algorithm consequently must be 25. Again, I extend my sincere apologies. If you guys watch that particular segment, then you will see that I made that mistake, and you should also make sure that you do not miss this particular step and account for it. Now let us get back to the problem S1M2. In that problem, as a reminder, we were asked to find a shortest path that an ant can traverse over the surface of a cube from, let's say, vertex A, crawl over that surface somehow, and arrive to the diametrically opposite vertex G in a shortest possible way. The specific names of the vertices of the cube do not really matter. What matters here is that if we pick any vertex, such as NA, the destination point must be diametrically opposite and sit on the other side of one of the cube's main diagonals. That problem seems to be difficult to solve. Out of the gate, it's not really clear how should we even approach that problem. Some people who know perhaps multivariate calculus think, that particular path will be characterized by a function perhaps in 3 variables, so maybe we have to investigate how that function behaves and try to find its extreme values. The people who know single variable calculus think, how can I fold that particular path from A to G into a function of just one variable, take its first derivative, equate it to 0, and so on. And the people who are familiar with the machinery of calculus of variations probably can see some vague but fairly close analogy with the so-called brachistochrone problem that was posed by the continental mathematician Johann Bernoulli in 1696, in which Johann Bernoulli inquired what is the shape of the curve that a material point must follow in order to arrive from one fixed point, call it G again, to another fixed point, call it A, in the shortest possible time, with the caveat that the bottom point here must be displaced horizontally from the vertical defined by the top point. So this distance must be different from 0. Obviously, in this problem, we need to optimize on time, but in our problem S1M2, we also have 2 fixed points. But here we need to optimize on space because we are required to find a trajectory from A to G, which is shortest in length. Now, in Season 1, Episode 1, we told you guys that mathematics is, again, an art of telling a story of how and why, and the objective here is to uncover a beautiful story that sits behind the problem S1M2 and that unlocks an elegant solution of that problem. In Season 1, Episode 2, we explained how to practice mathematics correctly, one correct way to practice mathematics, in which we suggested that in order to practice mathematics correctly, we can follow a four-stage process where in the first stage we understand the problem statement deeply and correctly. In the second stage, we fight the fight and stir our creative juices and think out of the box in order to generate a solution of the problem at hand. In the third stage, we reflect on the problem-solving experience. And in the fourth stage, we try to generalize and abstract the solution of the problem that we just generated. We also mentioned that initially you may get stuck fairly often while trying to solve proper mathematical problems correctly and on your own, and that you may have the temptation to watch our solution all the way to the end. At which point we recommended that you guys resist this urge and resist that temptation and only watch the minimum viable amount of information that we present that makes you go, aha, now I see what is going on. At which point we recommended that you put this video on pause, walk away from the computer, and try to solve the problem completely all the way to the end, correctly and on your own. As such, to the viewers who are still in the fight and who want to give the solution of the problem S1M1, we would like to give you guys a practically giveaway hint. If you follow that hint, then you may come across or discover a particular maneuver that will unlock a very elegant solution of the problem S1M2. In other words, we suggest that you guys make a physical model of a cube out of a heavy, or what is called here in US, a project paper. At which point we recommend that you guys put this video on pause, walk away, and then come back with a complete solution that you generated on your own. Welcome back. Now let's compare your ideas and ours. The reason why I gave the problem S1M1 and problem S1M2 in that particular order is because even though descriptively these problems seem to be different, technically or at their essence, these problems are actually very close to each other. As a reminder, in the problem S1M1, we ask you to find the length of the radius of a wholesome sphere when we are given a wholesome sphere. And in the second part of the problem, we ask you to do the same if we're given only a fragment of a broken rigid sphere. It turns out that both of these problems, Season 1 Math Problem 1 and Season 1 Math Problem 2, can be solved using one and the same problem-solving approach called transform and conquer. As such, before I explain to you guys what a problem-solving approach is to begin with, and before I explain the mechanics of how the transform and conquer approach works, I would like to give you a compressed view of the solutions of both parts of the problem S1M1. In the first part of that problem, we picked any 2 points on the surface of a given wholesome sphere. We generated 4 circles centered at these points, and these 4 circles intersected at 4 distinct points, at which point we observed that due to the way in which the spherical geometry works, these 4 distinct points have to or must sit on one and the same great circle of a sphere, which in that particular case also played the role of the circumcircle of a triangle that can be constructed on any 3 distinct points chosen from these 4 constructed in this particular way. However, at that point, the technical challenge was the fact that the triangle that we constructed that way was buried deep inside the sphere and was not accessible to our Euclidean tools. However, the way we overcame that challenge is precisely by transforming a difficult to solve problem into a setting where the solution of the transformed problem became very straightforward, if not to say very easy. How did we do that? Well, with the Euclidean compass, we measured the three distances of between the points that form the triangle. We moved that triangle into the Euclidean plane using the Euclidean tools. We found the location of the circumcenter of the congruent triangle, and the moment we knew the location of the said circumcenter, the distance from that center to any of the vertices of the congruent triangle locked in precisely the length of the rigid sphere that we were after in the first place. So fundamentally, the way we solved this particular problem is by finding a successful transformation that made a difficult, if not impossible to solve problem very easy to solve. In the second part of the problem, we drew a helper circle on the given fragment, and then we picked again any 3 points on that circle, and then we transformed that triangle again from the innards of the fragment into the Euclidean plane pretty much in the same way we did it in the solution of the first part of the problem. We recovered the radius of the circumcircle, or the radius of this helper circle, r. Then we picked any point P on the helper circle. We knew the distance between the point that played the role of the pole of the helper circle, and then we managed to reduce again a difficult to solve problem into a problem that was easy to solve, because now we had to construct a right triangle based on the length of a height of this triangle that is played, the role of which is played by this radius r, and given the length of one of the sides as p of the triangle. When we constructed this triangle, we located the diameter of the wholesome sphere, we cut the diameter in half, and thus we recovered the length of the radius of the wholesome sphere if we are handed a fragment of that sphere. Again, in this particular case, we actually did two transformations. First, we transformed a triangle from the innards of a fragment of a sphere onto the plane, and the second transformation, if you guys remember, was what? The second transformation was the rotation, book 3, proposition 31, was the rotation of the so-called book 3, proposition 31, or the Thales theorem, in 3 space around the diameter of the circle, which plays the important role in this theorem, according to which the angle in the semicircle is right. Now that we know the technical essence of the solutions of both problems, let me explain what a problem-solving approach is and how does the transform and conquer problem-solving approach works. Before I explain how the transform and conquer problem-solving approach works, please allow me to say a few words about what a problem-solving approach is in the first place. A problem-solving approach is fundamentally a description of how a given technical problem may be solved, on the one hand. On the other hand, you can say, Roman, look, a method and an algorithm is also a description of how a problem may be solved. So what is the difference across a problem-solving approach, a method, and an algorithm? Fundamentally, or essentially, the difference between an algorithm and a method and a problem-solving approach amounts to the quality of the guarantee of a solution of a particular problem at hand. In other words, an algorithm sits on one end of the guaranteed solution of a problem spectrum because an algorithm does guarantee such a solution, while a problem-solving approach sits on the opposite end of the guaranteed solution of a problem spectrum because it may sound a little funny, but a problem-solving approach really does not make guarantees of any kind. In particular, a computer science algorithm is a finite description of a finite number of steps that guarantee a solution of a particular computational task that can be carried out in a finite number of steps and in finite time without human intervention. A mathematical algorithm is also a finite description of a finite number of steps that a human can take in order to solve a particular problem within the well-delineated boundaries established by the particular problem at hand. For example, in the previous episode, we dealt with a mathematical algorithm that bisected a given line segment with the three curves, two circles and a straight line. What that means is that no matter which line segment you give us and the corresponding ambient plane to which this line segment belongs, then always, 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 under any conditions, as long as we have two properly functioning Euclidean tools, the Euclidean compass and the Euclidean straight edge, we can, in a finite number of steps, bisect that line segment, again, under any conditions. For a slightly more sophisticated example of a mathematical algorithm, consider the so-called Cauchy's residue theorem in its simplified form. According to that theorem, if f of z is a single variable complex to complex function that is holomorphic everywhere in and on a simple closed curve named gamma, then the contour integral of that function over that simple closed curve can be represented as the sum of residues of the function f of z evaluated at the poles of that function that are located inside the simple closed curve gamma, with that sum scaled by 2 pi I. Consequently, what are the two characteristic features or properties of an algorithm in that respect? Well, we see that on the one hand, an algorithm guarantees a solution of the problem, and on the other hand, the description of that guarantee is packed with mathematical jargon that is specific to this particular problem. For example, in the first case, we had to know what a point, what a straight line, what a circle, what a line segment, what a right angle is. And in the second example, we had to know what a function is, what the complex numbers are, what a simple curve is, what a closed curve is. We had to know what a residue is, what a pole is. We had to know what 2 pi and I are. For example, pi is the half period of the exponential function, and this funny looking symbol I is a generator of the group of the fourth roots of unity under multiplication, and I also has the property that squared yields -1, and so on. And in real time, it takes students actually several years before they can parse and comprehend all the terminology that is packed into this particular algorithm. So that means that an algorithm is packed with local jargon. Slightly below an algorithm, there sits a method which I moved a little bit closer to the algorithm than to the problem-solving approach because a method already does not guarantee a solution of the problem at hand, but if and when that method works, then such a method behaves like an algorithm. For example, let's say we're given a numerical sequence and we want to know, or we want to figure out the so-called closed form formula that predicts the shape of the next element of that sequence. In this case, we may use the so-called method of finite or common differences by constructing the corresponding differences between the adjacent terms and observing if that difference or differences converge or stabilize over one and the same number. Here, if a given numerical sequence is truly polynomial in nature, then yes, eventually these differences will converge or stabilize over one and the same number. And then we will be able to produce the corresponding polynomial that will predict the shape of the next element in the sequence. However, that information is not known to us up front. What if a given sequence is not polynomial in nature? Then the method of finite or common differences will simply not work, and it will not produce a solution of the problem at hand. Consequently, I moved a method slightly below an algorithm, but way above a problem-solving approach. Now, a problem-solving approach sits on the very bottom of the guaranteed solution of a problem spectrum because a problem-solving approach does not really make any guarantees of any kind that a solution of a given problem will be produced. What are the characteristic features or properties of a problem-solving approach? Well, a problem-solving approach is also a finite description, as we shall see very soon, of a finite number of steps that may lead to a solution of a problem, and that description characteristically has absolutely no professional or local mathematical jargon. In such a description, there will be no holomorphic functions, there will be no residues, there will be no simple closed curves, there will be no field extensions, there will be no quadratic residues, prime numbers, group normalizers, centralizers, and so on. That description will be done essentially in a very simple or common language. On the other side, the description of a problem-solving approach also does not provide any algorithmic guidance with the precision that is baked into the description of an algorithm. It may sound a little funny why even bother with problem-solving approaches if they do not provide any algorithmic guidance, but as it turns out, even in such a somewhat vague description, a problem-solving approach actually may help us solve problems not only in mathematics, but in theoretical physics, in computer science, and in computer programming. And the experience of seeing which problem-solving approach works in which particular case will come with time and experience. Now that we understand a little bit what a problem-solving approach is and how does it stack up against a method and an algorithm, let me explain the mechanics of the transform and conquer problem-solving approach. According to the transform and conquer problem-solving approach, we should try to find a candidate transformation that has the following three fundamental properties. Such a transformation should be reversible or invertible. That transformation should preserve the technical essence of the original problem, and that transformation should provide us with a tactical advantage or should make the process of searching for a solution of a perhaps difficult to solve problem easier or more tractable. Once we find such a candidate transformation, then the transform and conquer problem-solving approach prescribes that we solve the potentially easier transformed problem, and once we do that, we perform the final step and we do the reverse transformation of the transformed problem back into a solution of the original problem. Now, let us discuss at depth a little bit the three fundamental properties that a transformation should possess. Why does a transformation that may work under the transform and conquer problem-solving approach should be reversible, and what does it even mean? When we say that a transformation is reversible, that means in plain English that we should be able to film with the camera the flow, the forward flow of that transformation, and once that forward transformation is carried out, we should be able to play back that movie from the end towards the beginning, frame by frame, second by second, minute by minute, and all that playback should make sense and should not lose any relevant technical and essential details. Why do we need our candidate transformation in this case to be reversible? Well, we need that candidate transformation to be reversible because in the third step, we will be required to reverse transform the solution of a transformed problem back into a solution of the original problem. And if we cannot carry out that step precisely because the candidate transformation is not reversible, then what is the point of this whole exercise? Next, a candidate transformation should preserve the technical essence of the original problem. Why do we need that transformation to possess that property? Again, it's just common sense. When on the third step we will be performing a reverse transformation of the transformed problem, we will obtain a solution of something that may be different from the original problem. And yes, fine, we probably in this case solve some other problem if the candidate transformation does not preserve the original problem and alters it so much that it becomes totally different problem, fine, but we are asked to solve this particular problem and no other. Consequently, if the candidate transformation does preserve the technical essence of the original problem, then on the third step, when we flip that solution of the transform problem back, we will apply a solution of precisely the original problem and not some other problem. Lastly, the candidate transformation in this case should provide us with the tactical advantage or should make the process of searching for a solution of the transformed problem easier. Again, why do we need this requirement? Again, this is a common sense. If we cannot make the process of searching for a solution of a problem easier, then why bother? And what is the point of this whole exercise? Note that in my humble, unprofessional opinion, and based on my limited engagement with mathematics, theoretical physics, computer science, and computer programming, these three properties are essential or required, which means that if we throw any one of these properties out, then the transform and conquer problem-solving approach will become something else. I don't know what it will become, but it will not be a transform and conquer problem-solving approach. And on the other hand, if we add more properties to the candidate transformation, then that extra information will not affect the technical essence, the beat, the flow, and the fabric of the transform and conquer problem-solving approach. In general, I recommend that you guys remember the following several words when it comes to the transform and conquer problem solving approach, excuse me. Transform, solve, reverse transform. In essence, this is all there is to it. Now that we know a little bit the theory of how the transform and conquer problem solving approach works, let us see how we can apply that theory in practice to finding a solution of the problem S1M2. Here you guys can say, Roman, have you gone completely bananas with your problem-solving approaches, because none of these problem-solving approaches provide any algorithmic guidance to us when we are trying to solve a problem at hand. Here, I think that following a procedure that was already invented or constructed by someone else is not that interesting, and precisely working with an open-ended problem, trying and failing several times, or working precisely with problem-solving approaches is what makes mathematics interesting and exciting, and that activity is what precisely brings to light the fact that mathematics is an art form, because mathematics is an art of telling a story of how and why, and before we can put this story forward, we have to improvise and we have to think out of the box. At the end of season 1, episode 3, we ask you guys to at least give a shot to abstracting the solution of the problem S1M1, and we warn you that that task will be very difficult, will be challenging, because in order to accomplish this task successfully, you will have to think at a higher plane of abstract cognition. Consequently, if you were able to abstract the solution of the problem S1M1 successfully and on your own, and you manage to cleave away the irrelevant, in this particular case, details, and come up with something that resembles the transform and conquer problem solving approach on your own, you are doing well. Good job. Keep it up. Now, in this case of the problem S1M2, what successful transformation may unlock a very elegant solution of a seemingly very difficult problem? Well, as I told you guys in the hint, you can see that Roman has a cube over here. This cube looks a little flimsy, so you guys probably think that I'm up to something here, and yes, you will be 100% correct. I am up to something. The reason why this cube looks a little flimsy is because I hold it together with just two scotch tapes, and a successful transformation that unlocks an elegant solution of the problem S1M2 is the so-called step from the 3 space into the 2 space by using an abstract tool. Let's call that tool a mathematical knife, with which we make 7 careful cuts along the edges of a cube in such a way that we do not rip or we do not tear the material of the cube at any place, and we make these cuts in such a way that the resultant shape can be embedded completely and fully within the plane, with nothing sticking out of the plane. And the resultant shape, that is how we do that, the resultant shape that is produced by this careful cutting process, I'll put this shape on a blackboard in a minute, is called a net of a solid in general, or in this case, it will be called a net of a cube. Now let us go over the details of the steps involved in applying the transform and conquer problem solving approach to this particular idea, to this particular solution. First, let us try to answer the question of whether the transformation that we just came up with is reversible. Well, the answer to that question is yes, sure, it is reversible, precisely because we were careful to make the cuts strictly along the edges of our cube, and we made sure that we did not rip or tear the material from which the cube is made. Consequently, we can fold the edges and the faces of acquired net back into the original shape. If you guys be a little bit patient and hang with me here as I try to do it in real time, then we will obtain the original cube precisely in the form from which we have started. And in that sense, this specific property of a net of a solid can actually be a defining one. Which property is that? Well, that's the property that figures in the answer of the second question. Does the newly found transformation preserve the essence of the original problem at hand? What is the original problem at hand in this case? Well, the original problem in this case is fundamentally a cube. And what does it mean for a three-space object to be a cube and not a tetrahedron or a cylinder or a sphere or a dodecahedron? Well, that means that this particular polyhedron has 6 faces, each of which looks like a square, and these squares are put together in this particular way. And when we do produce a net of a solid or a net of a cube, we specifically make sure that we place our cuts along the edges of the solid at hand in such a way that, let me try to put this thing over here like so, see if it will stick. Yes, it does. So we try to produce a cutting of a given solid into a two-dimensional shape called a net in such a way that the number of faces in the resultant net is precisely equal to the number of faces in the original or parent object. In this case, we have 1, 2, 3, 4, 5, 6 faces in our net or two-space flat shape, and we have precisely 6 faces in a cube. Consequently, we can answer the second question in the positive because we claim that, yes, this particular net does preserve the technical essence of the original problem, because this particular net can be put together not only into just any good old three-space shape, but that particular net can be put back precisely into the original cube. Next, does the net that we just produced and consequently the suggested transformation provide us with the technical advantage? Well, the answer to that question is also positive. Why? Well, in general, our ant over here can begin its journey at the point A, wander around the plane, for example, executing a random walk any which way it wants, and then it can arrive at the point G. Can the ant do that? Yes, sure, but why? In this particular case, that is not required. Also, the ant can jump off the plane, somehow crawl around a three-dimensional space, and then again arrive at the point G. Can the ant do that? Yes, but what the ant can also do is crawl from the point A to the point G by staying at each instance of time precisely on the material from which our net is made. In other words, in this particular case, we remember that the minimizing geodesic, or a curve that minimizes the distance between any two points in a given space in the Euclidean plane, is what? A straight line. And if in the original difficult to solve problem it was really questionable how exactly does the trajectory of the ant from A to G must look like when it is in 3-space, in the 2-space case, that question is not really a question but a kindergarten variety task, because, let me see if I can do this in real time, all we have to do in this case is connect the lines A and G with a straight line, which is a task that is basically trivial to carry out because the three spaceness, or the main challenge of the original problem, is now removed by a successful transformation. What do we do now? Well, we go back to the description of the transform and conquer problem solving approach, and we see that once we check all the properties of a candidate transformation and we answer all these questions in the positive, all that is left to do is solve a potentially easier problem at hand, which we just did. And as the final and the third step, we are suggested to reverse transform the solution of the easier transform problem back into a solution of the original, perhaps difficult to solve problem. How do we do that? Well, again, remember, precisely because we answered all the testing questions earlier in the positive, we simply take our net. Let me see if it will come off nicely. We take our net of a cube that we produced earlier, and because it is reversible and preserves the technical essence of the original problem at hand, we put it back together using the anti-mathematical knife known as, let's say, a mathematical glue. Okay, hang with me, guys. We put our cube together, and in this particular case, the solution of the problem emerges all by itself. Now that we understood how the mechanics of the transform and conquer problem solving approach can be applied to this particular case, let us do a little bit of arithmetic and compute the length of that shortest path. When we cut our cube in this particular way, as I chose to do it here for demonstration purposes, then the names of the vertices of the given cube in the corresponding net will be partitioned in a way that is shown on the blackboard right here. And an interesting question is why? Well, let us think together. First of all, how many edges do two adjacent faces of a cube share? Well, it should be evident that two adjacent faces of a cube share precisely one edge. Consequently, when we choose to cut this particular edge with a mathematical knife in order to produce an advantageous net of a cube, that edge will split into how many distinct copies? That is correct. In this case, every edge of a cube that we do cut will split into two. For example, the edge AD was split into two edges shown here, AD and AD. But what about the names of the vertices of a cube? Again, let's think together. What is an interesting or a characteristic property of a cube in this respect? Well, every vertex of a cube has how many distinct planes or how many distinct faces meeting at it? Correct. Every vertex of a cube has precisely three distinct faces or three distinct planes meeting at that particular vertex. Consequently, when we choose to cut our cube in such a way that all three faces that meet at that particular vertex open up, then that particular vertex can be taken into three distinct vertices in the corresponding net. And that is the largest number into which any one vertex of a cube can be taken into. But a vertex of a cube with this particular cutting can also be taken into two distinct points, which is the case with the point G and G over here. Now, when we produce this particular net of a cube, then the solution path that our end can take from the point A in a straight line to the point G consists of two legs. The first such leg in this particular cutting or in this particular net will always lie through the face E, F, B, A. And the second leg of the shortest path will in this case lie through the face of the cube named F, G, C, B. Consequently, the straight line solution AG plays in this particular case what role? Correct. In this case, the solution path from A to G plays the role of a hypotenuse of two right triangles. The triangle AEG and the triangle MFG, where the point M is a point where the solution path AG intersects the cube's edge BF. Why are these triangles right? Well, we know that a cube is a polyhedron that has 6 faces, and each of these 6 faces is a square. And remember, through the exercise that we went through when we were dealing with the mechanics of the transform and conquer problem-solving approach, we showed that our net is a faithful representation of a cube. Consequently, every face, so to speak, of a net is also a square. And in a square, the adjacent sides meet each other at right angles. Consequently, the magnitude of the interior angles at E and at F are right. What else can be said about these triangles? Well, in this case, the interior angle at G, this one, is shared by both of the triangles, and consequently it is one and the same for both triangles. Early in his Elements, in book 1, I think, Euclid claims that the magnitudes of all right angles are the same, which means that the interior angles at E and F in these two triangles are also one and the same. Also in book 1, Euclid, in Elements, Euclid proves that the magnitudes of the interior angles of every planar triangle sum to pi radians, which means that if these two angles in both triangles are correspondingly equal, then the remaining angles at M and at A must be equal as well. And I marked these angles with a double line here so you guys can see it, like so. That means that by AAA, or angle, 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 the triangle AEG must be similar to the triangle MFG. In his Elements, in book 6, proposition 4, Euclid proves that in this particular case, in similar, or as he refers to them, equiangular triangles, the corresponding sides are in the same proportion. What does it mean in our case? In our case, it means that the distance from M to F is in the same ratio to the distance from F to G, shown here, is exactly the same as the distance from A to E to E to G, the distance from E to G. But we just agreed that every face of our net is a square, and the length of the side of each square is one and the same. We refer to this length as A everywhere. That means that the ratio of the distance from A to E to the distance from E to G is captured as A over 2A, or 1 to 2. If we cross multiply this equation right here, then we will see that twice the distance from M to F is the distance from F to G. But again, we're dealing with squares over here. That means that the distance from F to G is the same as the distance from F to B. And the distance from F to B can be made composite and assembled from two line segments. The line segment FM, this guy right here, and the distance MB, or the line segment MB. Consequently, if we equate twice the distance from M to F to this particular sum, we see that the distance from F to M can be cancelled on either side of the equal sign, and we arrive at the wonderful fact that the point M over here, where the solution path intersects the edge of the cube FB, is precisely the middle of that edge. We'll mark it with like so. This distance is the same as this distance, and we will use that fact very soon when we assemble our net back into the parent cube. Lastly, from the same right triangle AEG, we, by Euclid's Book 1, Proposition 47, or the so-called Pythagorean theorem, can recover the length of our solution or optimal path between two diametrically opposite vertices of a square, and simply write that that distance from A to G is a hypotenuse of the right triangle AEG, and that distance is a square root extracted from the sum of two squares, the square of AE, the distance AE, and the square of the distance from A to G, which come out to the length of the edge of the parent cube scaled by the square root of 5. And because we solve this problem generically, that means that that will be the case on any cube whatsoever. Now let us go back to the fact that the point M cuts the edge of the given cube FB exactly in half, and see how we can take that information further. What does it mean? Well, that means that when we assemble our net back into the parent shape of a given cube, then to produce other shortest paths between the vertices A and G on the cube, we do not really have to go through the same exercise of cutting, splitting open, drawing lines, and so on. Because we see that, for example, here, the initial leg of the journey, of the shortest journey, will go through the same face E, F, B, A, which on the three-dimensional rendering of the cube is right here. It turns out to be the bottom plane. What is it? E, F, B, A, this guy. And the second leg of the journey, the point also will be M, let's call it prime, because it will also cut the edge F, F, E in half. After that point, the second leg will run directly into the point G, and the length of that path will also be one and the same for exactly the same reasons. You guys should be able to prove it on your own. We have the same two right triangles, and so on. The arithmetic converges to the same number. So let us plot these two solution paths together. We start from the point A, and in the first case, we move towards the edge FB, this guy. This will be the point M here. We show that this first leg will be not visible. We show it with a dashed line. And then it's a victory lap all the way to the point G. Sorry, this way. So that will be the first path. A, M, M, G, A, M, M, G. The second solution path in this case will lie through the edge EF, which is this guy. So let's say this is the middle of this edge. That leg of the journey will not be visible. And from here, the end will shoot straight up. This will be the second leg of the shortest path in this particular case. Now, what can we say about the total number of distinct shortest paths between A and G? Well, that is relatively straightforward. We already know that at every vertex of a cube, how many distinct faces meet? 3 faces meet at every vertex of a cube, 3 distinct faces. In each such face, our friendly ant has how many choices for the first leg of the victory lap? Precisely 2 choices. And the number of choices, the specific choices that the ant makes for a one specific face does not affect the number of choices that the ant can make for the other faces of a cube. That means that in this particular case, the so-called multiplication counting principle applies, which is a very elementary combinatorial reasoning, and consequently we will have 3 initial choices, and for each such choice we have 2 more. It comes out to 6 distinct shortest path solutions exist for a given cube, and let us plot these guys together. First, let's say we cover the front face A, B, C, D. Here, out of the gates, our ant will have 2 choices. Cut to the middle of CB, this guy, or cut to the middle of CD, let's say this guy. So here he will go straight up and then to the point G, and in this case the ant will go to the middle and to the point G. In this case we can see both of the legs of the shortest possible trajectory for the ant. That's why I show them in a solid line. And I'll use the green color. I'm not sure if you guys can distinguish, but it's green. So here in this case, the ant will crawl through the face on our left, E, H, D, A. Here, out of the gate, the ant will have which 2 choices? Go to the middle of the edge HD, or go to the middle of the edge HE, let's say here somewhere. So he will crawl up from A to here, then over the top this way, and then he will crawl over the left face of the cube and through the back face like so. So this gives us 6 distinct shortest paths from one vertex of a cube to the diametrically opposite vertex of a cube. Now that we understand the arithmetic behind our solution, let us take a brief look at the properties of these solutions. What type of an interesting property can you guys spot when it comes to a solution trajectory of a shortest path from A to G? What do you guys think? Correct. That solution path or that solution trajectory possesses a property to which we can refer as symmetry. And symmetry is a very popular, deep, and important notion in mathematics because, for example, the so-called theory of groups is one gargantuan experiment in studying precisely that notion of symmetry. What does the notion of symmetry mean in our case? In our case, the symmetry of any one solution trajectory means that if our ant decides to travel from the vertex A to the vertex G in, for example, this particular blue path from A to the middle of the edge CB and then from that middle to G, then let's say our ant begins its journey from the point, from the vertex G, and backtraces its steps towards the same trajectory, but then it arrives to the vertex A. What do you guys think about the quality of that particular path? Correct. That particular path that the ant can trace from G toward A this time, but over the same path, will also be a shortest possible trajectory from the vertex G to the vertex A. And we know that 6 such distinct paths exist for what? Correct. 6 distinct paths, shortest possible trajectories, exist when we fix 2 vertices that are diametrically opposite on that particular cube. But how many such pairs, diametrically opposite vertices that is, does a cube possess? Well, in general, let me take the white one. In general, a cube has how many vertices? 8. Very good. Now, these 8 distinct vertices of a cube can be partitioned in how many pairs of diametrically opposite vertices? Well, the answer to that question is equal to the number of main diagonals of a cube. And the cube has how many main diagonals? Correctly, every cube has 4 main diagonals. In this case, let's name them. The diagonal from A to G, and in that same plane, the diagonal from F to D. That's 2. And in that plane that passes through C, H, E, and B, we have 2 diagonals also, the main diagonal from C to E and the main diagonal from H to B. Consequently, all 8 vertices of a cube can be partitioned into 4 distinct pairs, each of which belongs to the opposite side or the opposite edge of a main diagonal. So 8 over 2 gives us 4. And we know that for each of these 4 pairs, where we only investigated or analyzed a particular pair A, G, but all the other pairs will be analyzed in exactly the same way. Again, by the same multiplication counting principle, how many total shortest trajectories can be traced over a given cube? Correct. 6 times 4 equals 24. In other words, any given cube can be covered with a net of 24 shortest trajectories from one vertex of a cube to a diametrically opposite. Just for kicks, I'll show you guys, for example, I'm not going to do it for the entire cube. It will be very messy and incomprehensible. But as an experiment, let's say we cover the front face A, B, C, D of our cube with such network of first legs of the shortest trajectories. For example, from B, we'll go to where? To the middle of DC here, and then we'll go to the middle of AD like so. Then from the vertex C, we'll go where? To the middle of the edge AB like so, and then we'll go to the middle of AD like so, this way. Lastly, from the vertex D, we'll go to the middle of AB like so, and then we'll go to the middle of CB like so. So if we cover all the other faces of the cube with this particular legs of the shortest journey, then we'll have all 24 drawn on a cube. And I personally did not investigate the interesting mathematics that can follow from playing with this particular configurations drawn on a cube, but that is what mathematicians do. When they come across an interesting situation, they keep asking questions, and as you guys remember from season 1, episode 1, asking questions is what mathematicians do also, among other things. Here, for example, forget about the other shortest path, but if we stick with just one fixed family, for example, if we take this path, this leg, and the green one on the other side here, and let me dash that plane that is defined by this path. The interesting question that we may ask, if we cut our cube along the path from G to middle of CB and to A, and then from here to middle of HE to G, will we cut the volume of the cube in half or not? And if the answer is yes, can we generate a convincing proof? So that may be interesting, and that is how maybe a mathematical or interesting, or maybe not interesting, mathematical problem can be born. Lastly, another property of our solution trajectories is the following. You should, guys, try to do it as an informal exercise. I'm not going to number this as a separate problem, but just for yourself, because we're not doing what we're doing for money, for tests, or for grades. The only reason why we do what we do on this channel is because we want to gain a deeper understanding of mathematics, and that's how you gain that deeper understanding, by showing initiative and trying to investigate certain things on your own without me giving you guys an explicit homework assignment. I show over here two different nets, in the sense that the names of the vertices on these two nets are different, and you should try to come up with these two particular partitions of a successful net on your own, with the objective that looks like the following. In this particular net, I show the distribution of the names of the vertices of a cube when the first leg of the winning trajectory lies precisely through the face A, B, C, D. Consequently, in this particular cutting of a cube, our destination vertex G splits into two, this one, and the paths correspondingly shown here. But this particular partitioning of the names of the vertex corresponds to these blue paths over here, this guy and this guy, that lie through the front, through the facade of the cube A, B, C, D. The the net over cube shown over here at the bottom shows the partitioning of the names of the vertices of the cube in this particular case, that corresponds to the victory paths that go through the left side or the left face of the cube A, E, H, D. In this case, all the initial legs of both of these journeys lie through that particular face, A, E, H, D, and this is what I try to show you over here, A, E, H, D. In this particular case, it is interesting that the faces on which the point G belongs got split into three, G, G, and G. But in this case, we show these two guys only. And again, before you guys study these particular nets in detail, put this video on pause, walk away, try to do the right thing, think on your own, and then come back and compare your results with mine. This is almost it for this episode. In the next segment, I'll give you guys the next problem, and we will wrap this episode up. In order to ensure that you really understood the mechanics of the transform and conquer problem-solving approach, I have designed two really fun and really loose exercises for you, and one exercise that is slightly a little bit more formal, but still it's a relaxed and it's actually useful exercise in its own right. As such, to make sure that you guys can apply what you learned today to a realistic problem solving setting in a relaxed way, try first to take a good old A4 or office sheet of paper and throw it across the room, sending it, let's say, for the sake of the argument, 10 meters, 10 yards, or 30 feet out. Obviously, this is not that easy to do because the aerodynamic properties of a sheet of paper are not really that great for this particular task. And a challenge, should you choose to accept it, for you is to apply the transform and conquer problem solving approach to this particular fun exercise. In the next exercise, I suggest that you guys take your mother's favorite colander or a sieve. Make sure I don't spill anything. A colander or a sieve, and fill it up with water, and also carry that water across the room, making sure that your parents do not yell at you. Make sure that you can carry that water in the sieve also, let's say the same 10 yards, 10 meters, or 30 feet out. That's the second fun exercise. And the third fun exercise is slightly more formal. Here we suggest that if you are given an unsigned integer called x, then you should write a little bit of, for example, C-like code that detects whether that particular unsigned integer is a perfect power of 2 or not. In other words, your code should look at the unsigned integer x and return true if that integer has the shape of 2, 4, 8, 16, 32, 64, 128, 256, 512, and so on, if it's a perfect power of 2. And it should return false if the unsigned integer x is not a perfect power of 2. Again, as a hint, in all these three fun exercises, the transform and conquer problem-solving approach figures in an actually serious way. None of these problems are a joke, especially this one. This problem can be solved, and I'm eager to hear from you guys how you managed to solve this problem in the next episode. But an official problem for the next episode will be S1M3. In this particular official problem, our inquisitive ant will also travel over the surface of a cube, but this time the ant will begin its circumnavigating journey, specifically not at a vertex, but at a certain point that is displaced from any of the vertices of a cube and is located, as shown here, somewhere on the edge of a cube. Exactly where, it doesn't matter, as long as the initial point P is not a vertex of a cube. The intellectual challenge in this particular problem is to find a path, the shortest path, that the ant can take in order to circumnavigate the entire cube and visit each face of a cube, and then also make sure that that path is the shortest possible out of all the circumnavigating paths. This is it for this episode. Thank you very much for staying with us. Thank you for your time. I'll see you guys in the next episode, where we will discuss the solutions of the fun exercises and the solution of the official problem S1M3.